Today, we're going to prove something really cool using mathematical induction. We're going to show that for any natural number n, when you add up the fractions 1/2 plus 1/3 plus 1/4, all the way up to 1/2 to the power of n, the sum is always greater than or equal to n/2. This might sound complicated, but I promise, by the end of this video, you'll completely understand it. Let's dive in. First, let's understand what we're trying to prove. We have a series of fractions. It starts at 1/2, then 1/3, then 1/4, and it keeps going until we reach 1 divided by 2 to the power of n. The question is, does this sum always give us at least n/2? That's what we need to prove. And we're going to use a technique called mathematical induction. Mathematical induction is like climbing a ladder. First, you prove you can get on the first rung, that's the base case. Then, you prove that if you can stand on any rung, you can always step up to the next one. If both of these are true, then you can climb as high as you want. Let's apply this to our problem. Let's start with the base case. We set n equal to 1. On the right-hand side, we get 1/2. Now, for the left-hand side, we need to add up all fractions from 1/2 to 1/2 to the first power, which is just 1/2. So we only have one term, which is 1/2. So 1/2 equals 1/2. The inequality holds for n equals 1. Our base case is proven. Now, we move to the inductive hypothesis. Now, for step 2, the inductive hypothesis. This is where we make an assumption. We assume that our inequality is true for some natural number k, so we're saying, okay, let's pretend this formula works when n equals k. We write it out, 1/2 plus 1/3. All the way to 1/2 to the k is greater than or equal to k/2. Remember, we're just assuming this for now. Here's where the magic happens. We need to prove that if it works for k, then it must work for k plus 1. So we're looking at the sum that goes all the way to 1/2 to the power of k plus 1. But here's the key insight. This sum can be split into two parts. The first part is just our sum for k, which we already assumed is at least k/2. Now the second part is for k plus 1, and we keep going. The new terms start at 1/2 to the k plus 1, then 1/2 to the k plus 2, then 1/2 to the k plus 3. And they continue all the way to 1/2 to the power of k plus 1. These are all the extra fractions we need to add. Now, we need to figure out how many new terms we're adding. The first new term is 1/2 to the k plus 1. The last new term is 1/2 to the k plus 1. Wait, that sounds confusing. Let me clarify. Let's use an example to see exactly how this works. If k equals 2, we had terms up to 1/2 squared, which equals 1/4. For k plus 1 equals 3, we go up to 1/2 cubed, which equals 1/8. So what are the new terms we're adding? They are 1/5, 1/6, 1/7, and 1/8. Notice that the first new term is 1/2 squared plus 1, which is 1/5. And the last new term is 1/2 cubed, which is 1/8. To count how many new terms we added, we take 8 minus 4, which equals for new terms. So we added exactly for terms, and for equals to squared, which is 2 to the k. In general, the number of new terms equals 2 to the k plus 1, minus 2 to the k. Now, using our index laws, 2 to the k plus 1 can be rewritten as 2 to the k times 2 to the 1. So we have 2 to the k times 2, minus 2 to the k. Let's factor out 2 to the k. This gives us 2 to the k times the quantity 2 minus 1, which simplifies to 2 to the k times 1. And that's just 2 to the k, so we're adding exactly 2 to the k new terms. Now here's the clever part. Among all these new terms, which one is the smallest? Remember, with fractions, the bigger the denominator, the smaller the fraction. The biggest denominator in our new terms is 2 to the k plus 1. So the smallest fraction is 1/2 to the k plus 1. Since every single one of our new terms is at least 1 over 2 to the k plus 1, and we have 2 to the k of them, the sum of all the new terms must be at least 2 to the k times 1 over 2 to the k plus 1. Let's simplify this. 2 to the k divided by 2 to the k plus 1. We can rewrite the bottom as 2 to the k times 2. The 2 to the k's cancel out, and we're left with just 1/2. So the sum of all our new terms is at least 1/2. Now we put everything together. Our sum for k plus 1 equals our sum for k plus all the new terms. From our inductive hypothesis, we assumed the sum for k is at least k over 2, and we just proved the new terms add up to at least 1/2. So the sum for k plus 1 is at least k over 2 plus 1/2, which is greater than or equal to k plus 1 all over 2, and that's exactly what we needed to prove. The inductive step is complete. And we're done. We proved the base case works for n equals 1. We proved that if it works for any k, it must work for k plus 1. Therefore, by mathematical induction, this inequality holds for all natural numbers. This means no matter how large n gets, this beautiful pattern always holds true. Pretty cool, right? If you found this helpful, please like and subscribe, and let me know in the comments if you'd like to see more proofs like this. Thanks for watching.